Hi, so in this video we are going to discuss about LTI filters, and we'll look at two kinds of filters: finite impulse response and infinite impulse response filters. So what are filters? Basically they are used for changing my input signal x of n in a useful way. We have seen amplifier is a filter, noise filter is a filter, etc., etc. Now these filters are, if they are linear time invariant, that is the class of filters which we are looking at and which are very useful because we can characterize them with a transfer function, let's say h of z, and then we can design the shape of this transfer function so that we can attain the desired characteristics, which means we can obtain in what way we want to change x of n. We can design that. So this h of z, as you have seen, it has a gain, and then gain means the magnitude response and phase response. These two things we have seen, and then we can design my hz specifically for a particular task. Task here means in what way do I want to change x of n. And now we'll see two kinds of filters: finite impulse response filters and infinite impulse response filters. So what are they? So in short, they are called FIR and IIR. When they have a finite impulse response, which means my h of n is a finite signal, which means it is limited in n, which means that after a certain capital N, all the values are 0 for hn. Similarly, on infinite impulse response side, my h of n will not be 0 even after any large capital N, which means basically it could be asymptotically 0, but in principle it need not be exactly 0. Okay, then how do we see it in hz terms? Like in terms of h of z, what does that mean? In h of z, we characterize h of z with poles and zeros generally. So if there are no poles and only zeros are allowed, this is an FIR filter. There are no poles, only zeros are there, then it is an FIR filter. It makes sense, right? Your h of z has only the numerator part, and when you take the inverse z transform, your h of n will be a finite thing, basically with some delays like h of n minus n1, n minus n2, all those delta n minus n1, delta n minus n2. In this way, you get a finite h of n if there are no poles in h of z. But here we can have poles as well as zeros. So as soon as I have a pole, like let's say 1 upon 1 minus alpha z inverse, you immediately know that the transfer function will be like alpha to the power n un, like of that kind of a form. And then how do we see this FIR and IIR filters in terms of LCCD equations? In LCCD equations, there will be no feedback term. Like y of n will not be a function of previous y's. Means y of n will be function only of xn, x minus 1, x of n minus 1, x of n minus 2, etc. But it won't be a function of y of n minus 1, y of n minus 2, etc. So there is no feedback in LCCD equation. Whereas for an IIR filter, there is a feedback in LCCD equations. So basically, you can see IIR filter is more general. It allows for poles, it allows for feedback, etc. Now let's look at an example of an FIR filter. Let's take h of n as 1 upon 2, 1 upon 2. For n equal to 0, it is half. For n equal to 1, it is half. I think you can correlate it with the moving average kind of filter with your length as only 2. Now this h of n is, if I write it in terms of what do you say, impulse response, delta function, a Kronecker delta function, it can be written like this. Now let's look at the transfer function. Now h of z will be what? This is 1 upon 2, and you know, for delta n the transfer function is 1, for delta n minus 1 the transfer function is z to the power minus 1. So you get the term 1 plus z inverse. Now e to the power j omega will be e to the power j so minus j omega upon 2, and then cos of omega upon 2. You know, you can simplify it as this. Now let's try to plot how it looks like. So my h of z will be like this. Basically I have a 0 only in the numerator. You can see I have a 0 at minus 1, and then if I plot h e to the power j omega, you can also plot it, like sketch it by looking at the pole 0 plot, but also you can plot this term which looks like this, right? So either way you can plot, but the plot looks like this. There is a 0 at plus pi minus pi, and at omega equal to 0 the value is maximum, but not because of a pole, but just because of nothing nearby. So this is what is my simple FIR filter. And what kind of filter is this? It allows smaller frequencies. Okay, ignore the negative part, just look at the positive frequencies from 0 to pi. It allows lower frequencies, and it suppresses the higher frequencies. Higher frequency means close to omega, close to pi. So this is a low pass filter. The question is, how can I convert it into a high pass filter? I hope you can guess it very well. So here we are. So you look at this plot, and basically you want to pass the higher frequencies, cut down the lower frequencies. So just shift it by pi. If you shift the whole thing by pi, then it will be a low pass filter. It will be a high pass filter. So this means my the new h e to the power j omega will be equal to h to the power j omega minus pi, right? That is what is shifting in the frequency domain. Now this is equal to see this e to the power minus j pi is simply minus 1. So e to the power minus h minus e to the power j omega. So my new h will be this. Now how do I... Okay, so therefore my h high pass, the new h high pass z, the new transfer function, is simply equal to h of minus z, where h of z is this low pass one. So h of minus z, and if I substitute it in this, then I get simply this, and that's a high pass filter. Now this means my h of n for the high pass filter, my impulse response for the high pass filter will be what? You can simply take the inverse z transform, and which is very simple. It is simply half and minus half. That's it, right? And yeah, you can plot the for this one, you can plot the pole 0 plot. You see there is a 0 at plus 1. That's it. So basically you have taken a mirror image of this. You just take a mirror image, because what is this operation? Hz equal to h of minus z. So this is basically taking a mirror image along the y-axis, and no, not along the y-axis. This is about the origin, right? Plus becomes negative. Yeah, this is a mirror image about the origin. So let's now move on to the next topic. We have defined high pass and low pass filters, but how do we measure the magnitude of a filter? So this is a scale which we use. It's called a decibel scale. So basically magnitude is mod of h e to the power j omega, and if I want to measure it in decibels, you just scale it with this function, 20 log to the base 10 of this thing. and whatever value you get, that is the magnitude in dB scale, basically logarithmic scale. And if you write the whole thing in terms of power, basically power is magnitude square of h to the power j omega. And in terms of power, so this is the amplitude and this is the power. So square term is the power. So you can simply see that, take the 2 here, 2 log something is log something to the power 2, right? So just take the 2 here and the whole thing is exactly same, just it's 10 log power. Now let's look at this an example h of z. We have a pole at 0 and a 0 at -1, and if I plot it, there is a 0 at -1. So what do you think it will be? So at pi it is 0, so which means it is a low pass filter. It's a low pass filter. And now what do you get? This is my magnitude response or the gain in a linear scale. But if I write it in dB scale, how will it look like? So basically the 1 will become 20 log 0, which is 20 log of 1. Log 1 is 0. And here 0 log 0 is -infinity, and you can see it goes to -infinity. So this is how it looks like. Now let's quantify when we say low pass and high pass, what is the meaning of passing certain frequency? Because see, it is a continuous scale. Like, can you say it is passing this frequency? You can say it's a large value of gain, so it is passing this frequency. But when do you say it is not passing? What is the value where you will say that after this frequencies are not passed? So the convention is to see where the power is half. So wherever the power becomes, wherever the power is more than half, that is the region you say it is passing. And wherever the power becomes less than half, there you say it is not passing that signal, or it is curtailing that signal. So this helps us to define a term called cutoff frequency or half power point. Cutoff frequency is that frequency which marks this transition where the power goes from more than half to less than half. Basically the power becomes half, and this is called cutoff frequency or half power point. Now let's see how does it look like in the dB scale. So okay, this is my general equation for a half power point. At the omega cutoff, my h to the power j omega square is equal to half of the maximum value of h to the power j omega mod square. So when this is half, we get a cutoff frequency. And if I write it in terms of amplitude thing, and then it is 1 upon root 2. Now I am interested in knowing what is the dB thing. So let's convert the whole thing in dB, like the whole, take 10 log 10 of the whole equation, and you get this. Now you can this is simply the amplitude in dB or power in dB, right? And this is the power in maximum power in dB. But what do we do with this half term? So you just take this half out. Log of a plus b is log of a into b is log of a plus log of b. And this is now the maximum power. So the power at the cutoff frequency in dB, maximum power in dB, and what is this term? It's a constant term, which is -3. So that is why, so if you go to the log scale, there, whatever is the maximum value, just go 3 steps down, 3 dB under this, and that will mark your cutoff frequency in the dB scale. That's why this this value 3 is also called 3 dB point. Basically the omega c is called a 3 dB point. The cutoff frequency is called a 3 dB point because this is the frequency where the power is 3 dB less than the maximum. Yeah. Okay, so now let's look at some examples. This is an h of z, and how does it look like? You can see that there is a pole at alpha and there is a 0 at -1. Can you guess what is this? Is it a low pass filter or high pass filter? Is it an IIR or FIR? The answer is it is an infinite impulse response filter, an IIR filter, because there is a pole present here. So it is an IIR filter. Now, what can you say about whether it is low pass or high pass? Since pi is 0, at omega equal to pi, the magnitude will be 0. So we say it is a low pass filter. Okay, this is a low pass filter, and the maximum value will be obtained where at omega equal to 0. Basically, let's see this. So we have, let's make a rough plot. Here, the denominator is this length, and the numerator is this length. Numerator is large, denominator is very small, so the overall value is very large. And as you move away, your denominator becomes larger and larger, and numerator becomes smaller and smaller. So basically the overall function becomes smaller and smaller. So this is how it's a low pass filter, an infinite impulse response low pass filter. And what we find here is that you have at this point it is 0 at pi, and at 0 it is maximum value. Now you have to find the value of k so that your maximum gain is unity. And what is the maximum gain? It is basically here at omega equal to 0. So maximum at omega equal to 0. Now let's put the values. So my h e to the power j0, the value here, is equal to k 1 plus 1 upon 1 minus alpha times 1. Right, and we want this to be equal to 0. Okay, what is this? Basically, this is simply 2k upon 1 minus alpha. K is positive, and this thing should be equal to 1. So what should be the value of k then? So this means my k should be equal to 1 minus alpha upon 2. That's it. So if this condition is satisfied, then this is the maximum gain will be unity. And this is an IIR filter, IIR low pass filter. Okay, now let's analyze this filter in terms of cutoff frequency, etc. Because when we are designing a filter, what we are interested in, what is the cutoff frequency? Let's say somebody asks me, please design a speech filter which will cut off all frequencies above, let's say, 2000 hertz or above 1000 hertz, or somebody designing a power filter, and he will say, okay, cut off all frequencies which are above 50 hertz or above 60 hertz, let's say. And we can see that I need a relation between my cutoff frequency and the parameters in my filter. So in this filter, what are the parameters? Alpha is the only parameter. So what is the relationship between cutoff frequency and that filter parameter? That is what I have to find. So it's very simple. Let's write down the definition of cutoff frequency. Our definition of cutoff frequency omega c is basically h e to the power j omega c whole square should be equal to half times maximum of this value whole square, and we know that the maximum is 1 in this case, so it simply becomes 1 upon 2. Yeah, now let's plug in these values, and I want to find at what omega c is the value half. Okay, so just put this value, put this thing here, 1 minus alpha whole square upon 4 times, this is basically you have to do mod square. So this times the conjugate of this. So this is 1 plus e to the power minus j omega c times the conjugate of this. So 1 plus e to the power plus j omega c. Similarly, the denominator also, first the h to the power j omega, then h to the power minus j omega, the conjugate. Now we have to make this equal to half, right? This whole thing should be equal to half. And let's derive the value, like how it looks like. I'm just writing this whole thing again. Now let's focus on this term first. So what is this term? Just simple multiplication, and you get 1 plus then this multiply 1, and then you do the cross multiplication, e to the minus j omega c plus e to the power j omega c. It's twice the real part, it's twice cos omega c. And similarly in the denominator we get 1 plus alpha square minus twice alpha cos omega c. So same way, and this should be, now put this in the whole equation, the whole thing becomes like this. Now this is the thing, I'm just plugging this value in the equation and writing, like rearranging the things. And if we on simplification we get this alpha square cos omega c minus 2 alpha plus cos omega c is equal to 0. This is the design equation, or the relationship between omega c and alpha we get. Let's try to simplify it. It's very easy to find the value of cos omega c on left hand side and everything alpha on right hand side. This is one way to write the whole thing, but this gives us the relationship. But let's say if I given an alpha, how do I find an omega c? Or given an omega c, how do I find an alpha? Okay, given an alpha I can find omega c from here, but the other way around, when I'm designing it, in the design part, I know the specifications, what is my cutoff frequency, but I don't know my filter parameters. I want to find the value of alpha given omega c in the design while designing the filter. So therefore we have to solve it in a different way, where I want to find the value of alpha in terms of omega c. It's a quadratic equation in alpha, so just to use the solution of a quadratic equation, and that's the simple thing. All of you know that. And now if I simplify it, it simply becomes 1 minus sine omega c upon cos omega c. There could have been 1 plus and 1 minus, plus minus, but since I know my alpha should be less than 1, right, because I want my pole to be inside this unit circle, so that my system, so that the DTFT exists, which means my system is stable. DTFT exists when my unit circle is within the ROC. To keep the unit circle within ROC, I should place my pole inside the unit circle. So therefore I took this value, the negative sign only. Now this is my design equation, this whole thing, this is my design equation, right? So here we saw one example of a low pass filter, IIR low pass filter, and how do we design it given the specifications. Now let's look at an example of IIR high pass filter. So let's do the pole zero plot. This helps you to understand the whole thing. You see, at zero frequency, your value is 0, your magnitude will be 0, right? So basically you're cutting off the lower frequency, and then as you move up to pi, your value increases, and the maximum value is obtained at pi. So now imagine if you would have just taken a mirror image about origin, then this alpha would have shifted here, but that would also have been a high pass filter, but here this is also another high pass filter. But this high pass filter derives from the low pass filter in a different way, and you can derive the design equation. It will be exactly same as my low pass filter, but here the thing which I wanted you to note is that now h of hp e to the power j omega is not hlp minus e to the power j omega. That would also have been a valid high pass filter, but this is little different. This is 1 minus the low pass filter, and this is also a high pass filter, a valid high pass filter, but a different high pass filter. Okay, now we saw low pass filter, high pass filter, and let's also look at a band pass filter. So what is a band pass filter? Basically it allows only a band or a range of frequencies to pass. So anything lower than that range and anything higher than that range, they are curtailed or they are suppressed. So the shape will look like somewhere peak in the middle, and for that to happen I have to use second order equations. Notice that earlier we had only first order in Z inverse, now it is second order in Z inverse. So let's plot the pole zero plot and then things will be very clear to you. So what are these values? This is 1 minus Z square, Z to the power minus 2, which means 1 plus Z inverse, 1 minus Z inverse, right? I can write it like this. And this means I have a 0 at minus 1 and a 0 at plus 1. And if you look at the denominator also, then what we get is it will have two roots, and these roots will be complex conjugate, because this whole thing is a real thing. Alpha is a real, beta is real, and therefore the solution will also be a complex conjugate solution if it is a complex solution. So what we get here is, let's say the solution is 1 minus r e to the power j theta and 1 minus r e to the power j minus j theta. Now see, there are these two poles. These two poles are complex conjugate of each other simply because all the coefficients are real. Therefore we get complex conjugate solution here. You also know it from the solution of a quadratic equation. You get plus minus that term, and so let's now plot it. So this is how it will look like. You have got zeros at plus 1 and minus 1, and then two complex conjugate poles with the magnitude r and angle theta and minus theta, complex conjugate. Now what is the relation between this r theta and alpha beta? Let's if you derive it, it's very simple derivation. You can do it on your own. R is simply under root of alpha, square root of alpha, and my cos of theta is equal to so now I'm also interested in finding out where is the maxima obtained in my h to the power j omega. It is a band pass filter. You can see it is 0 here, it increases, reaches a maximum value, again decreases, again becomes 0 here. So it allows a band around here. There is a band which has power more than half, and other than that power will be less than half, and power will be 0 at 0 and pi, omega equal to 0 and omega equal to pi. Now maximum of h to the power j omega is obtained at omega naught, and this omega naught is equal to cos inverse of beta, and you can derive that from here. And the bandwidth. Now what is the bandwidth? It's a 3 dB bandwidth. What is 3 dB bandwidth? It means the power is above half, is more than half of the maximum basically. And so what if you derive it, the beta will come out to be equal to cos inverse 2 alpha upon 1 plus alpha square. You can memorize this result, or you can derive it. Derivation may be a little involved. So basically what I want to say is, this is how it will look like. My plot looks something like this. There is a peak at omega naught, and the peak will be 1 here. Oh, actually this is a plus sign here. Oh, I'm sorry. Okay, so this is another filter where basically you have a band stop filter. So what is a band stop filter? It is, instead of allowing a band, it is stopping only a small band and allowing all other frequencies. How do we derive it? If you look at the pole zero plot, the pole zero plots looks something like this. You have got this. You want to have a what do you say? You want to have a zero somewhere in the middle where you want to stop the band. So you have a 0 around this frequency, and around this there will be low power here, and the high power here. And by designing my alpha and beta parameters of the filter, I can control where do I want to put my things. And in a similar way, you can derive the equations for this one also, but this was just for your understanding that we have 4 kinds of filters we have discussed: high pass, low pass, band pass, and band stop. Thank you very much.